All right, so let's consider our matrix here in problem 30 in 2.5. So we're supposed to prove that A is invertible if A is not 0 and A is not B. And we're supposed to either find the pivots or find A inverse. And then we're supposed to find three numbers so C is not invertible. Okay. Um, hmm. Which one do you want to start with? Do you want to start with taking this in order, or do you want to start with this? Start with matrix C here.
I think I have matrix A because I found the pivots.
Okay.
Yeah, so if we could do C.
Okay. So yeah, let's start with matrix C here. So if we want three numbers so that C is not invertible, I think I need to spend just a second and drill on what invertible means. So what are some criteria for failing invertibility?
For this one, that would mean like there aren't three pivots.
Okay, yeah, we could look at the number of pivots. Another thing we could do is we could look at the linear independence of the rows or the columns, right? You guys with me on that? I think I see one really easy way to make C singular, right? Not invertible, which is to make two of the columns the same numbers. Right? If I can, or two of the rows. If I can make two of the rows the same numbers, then I can just say, hey, it's not invertible because one of the pivots is going to be 0. You guys with me on that?
Okay.
Okay, so how do I do that? What number do you pick to make two of these rows identical?
2.
Yeah, 2 does it. So I'm looking at that top row and I'm saying, hey, if all these C's in that top row were 2, the whole row would be 2. And then this whole second row would be 2. So C is 2 is one of my numbers. Do I see another one?
Assuming C can't be 0.
Oh, that's a great one. You guys see that? Like if C is 0, then this matrix has a column full of zeros and a row full of zeros. So then it'll be automatically linearly dependent. Okay, so C is 2 makes two of the rows the same. C is 0 makes one of the rows 0. All right, now what else? Got another one? Maybe the columns? How do you make those columns linearly dependent?
C equals 7.
Yeah, I think 7 will do it. For the same reason that 2 would for the rows, right? Okay, now, quick weird question. Is this all the numbers? This is actually a hard question to answer. Feels really tough. Like, did I find them all? Are there 3? How many could there be? All right, so let's think about that a little bit. One of the ways I could check that this matrix is singular, right, is I could calculate the determinant. You guys with me on that? Okay, so if I calculate the determinant, I'm thinking like, all right, how many C's could there possibly be in that equation? Like one thing you could do is you could actually go out and calculate the determinant here. You guys see that?
Yeah, and then you can see where the C's are, and then you can be like, okay, so if I have this number here, then it won't work.
Yeah, so if I go out and calculate this determinant, I'm going to get 2 times the determinant of the little submatrix with CC, 7, and C, right? And then I'm going to get minus C times the determinant of the little submatrix CC, 8, and C, plus C times the determinant of the little submatrix CC, 8, 7. You guys with me on calculating that determinant? Okay. Now, a little bit of weirdness. Those little subdeterminants I can calculate. So I'm going to get 2 times, well, this one's going to have like c squared minus 7c. And then my next one's going to have minus c times, oh, these parens and c's are going to be bad together. What do you get out of that little submatrix?
C squared minus 8c.
Good. C squared minus 8c. And then out of this last one, I'm going to get c, and that's going to be 7c minus 8c there.
I know we went over determinants like this in Calc 3, but did they show us how to do it in this textbook so far?
Oh, that's an interesting question. I thought so.
I don't remember reading about it.
Well, I
they
may have just given you a tool from the end.
Yeah, they showed us briefly a trick for doing it for 2x2 matrices, but I don't think it was anything larger than that.
Oh, okay. So yeah, I went ahead and stole a trick. You could do this with pivots too, but I think it's easiest to see here. Feel free to use this trick if you want. So if you want to know how to calculate the determinant of a 3x3 matrix, you do this, and yeah, feel free to use that. I'm gonna assume you guys can do that.
Joe.
Yes, sir.
Could you go a little farther into how you choose like your C's and your 7 and your 8 and your C's and everything?
Oh, where did I get this thing from?
Yeah.
Okay. So what I did is for this first one, I picked this 2 here. And then I crossed out the row and the column that it was in.
Okay.
And then I have that other little submatrix there. So that's what appeared right here.
Got it.
Okay. And then I did that exact same thing for the next one.
Okay.
So the next one, I picked this C, and then I crossed out the row and the column it was in. And I got that little submatrix. And the only hard thing about this is that you have to remember that when you're going across, they alternate sign. So I did plus the first one, minus the second one, plus the third one.
That's kind of like what we learned in Calc 3 about, I want to say, cross product of some stuff I minus some stuff J plus some stuff K.
Yep. Yeah, this is exactly the same formula that we use for the cross products. This is called the cofactor method of calculating the determinant. I'm only about halfway committed that you know this right now. You don't really have to. There are other things you could use here, but I find this to be a clever little tool here. So if you want to learn it, I encourage you to. You will have to learn it by the end of the course anyways. So I would throw it in your head now. The point of this whole process was that thing that I got at the end there is a polynomial. What degree is that polynomial?
Second.
Third.
Yeah, that's a third degree polynomial. Specifically, I've got a c times the c squared. And that means that this thing might have 3 zeros. The zeros are when it's not invertible. It can't have more than 3 zeros because it's only a third degree polynomial. So I have, in fact, found all 3 C's where this fails to be invertible.
Nice.
You guys with me on that? If you FOIL this thing out, you'd get a polynomial. You could set it equal to 0 and solve it, and you would get the same C's. You guys cool with that? There are a lot of ways to approach most of the problems in this textbook, which is one of the things that I find really fun about this course. So if you're approaching problems and you're not and you feel like you're getting somewhere, but it's not exactly the same thing I'm writing down, it's entirely possible that you're correct. Feel free to, reach out and offer an alternate solution if you want. It's all good.
So just to clarify, an n-degree polynomial, when we're doing, or when we're trying to find what numbers make it not invertible. So an n-degree polynomial means that there are n number of c's that make it not invertible.
Yeah, because they're the zeros of the polynomial, and a polynomial can only have as many zeros as it has degree. It may have less, but it can have at most. Okay. We could do this same kind of thought for A, showing that A is invertible. Or we could manually calculate the inverse using, I mean, personally, that's what I'd be doing. So if I was to do the kind of A part here, which Jacob didn't ask about, so I'm only going to briefly say, I would take my matrix, augment by the identity matrix, and do row operations to get the identity matrix on the left. That's going to put my inverse on the right. And in the process, I should see that I'm only going to be able to complete that procedure if A is not 0 and if A is not B. You guys with me on that? I can certainly see that if A is 0, this thing is not invertible. And if A equals B, it's not invertible. You see, I kind of get that for free. All right. Questions on this?